Thank you, Van. Thank you, Alex and Jeff, for organizing this very interesting mini-symposium. And one of our Copper Mountain luminaries showed up here, Tom and Teufel. Thank you very much for starting this over 14 meetings ago. So thank you very much, Tom. All right. So what's my goal? All right. So what you'll see is some permutation of this graph, right? So it's got 500 rows, 500 vertices. Permute the first 500 integers and apply that as a permutation to this. You'll get, a scatter plot. And from that, somebody turns around and says, hey, these are the groups, right? So what I'm interested in considering is what that person they're providing is anything more than a random number generator, right? Is there actually reason to believe that they've generated a community structure? For those of you who aren't so familiar with this literature, there's a lot of computer science literature, people pushing out all sorts of algorithms with very little analysis. And what's very unfortunate, there's very little assessment of how to evaluate whether the results are correct. So I'm trying to get interested in that. So that's a slightly tougher problem. James, thank you very much for setting the stage for picking a nice model problem. So I want to investigate this problem for the symmetric two-block stochastic block model where we could have variable block sizes. Okay, and again, what's the goal? Somebody, for example, uses a spectral method or some variation, and they say, oh, these are your two blocks for an undirected graph. Should we believe them? Certainly in this case, this seems plausible, right? If they didn't nail it, they're pretty close. But if those off-diagonal blocks were a lot denser, then you're not going to be able to turn this visibly. So how would you determine this? So that's going to be my talk. Okay, so some related work. The computer science and statistical physicists have thought a lot about optimality and recoverability for this sort of model, and that's kind of the theoretical computer science question is, does there exist an optimum? What are the limits of any possible algorithm to get these clusters? Okay. More statistical in nature are the last three bullets. A lot of work you see from the dates has been coming out in the last few years. In fact, some very, very good statisticians are now starting to get involved in this. And just in the last few months, some interesting papers have come out. So I've been doing this work and learning statistics at the same time while these papers coming out. Okay, so again, I think I already alluded to this. So my motivation for all this is I got involved with several people in the audience here to try and provide a computational spectral graph theory. And especially those of us that were used to computing eigenvalues and eigenvectors related to differential equations, we were there, you can assess your result. How do we assess these results? How do we know that the eigenvector is accurate, or what does that mean? Okay, so I got very interested in that, right? So certainly the question that James and Jeff addressed is, let's say the question that precedes this is, when should you terminate some sort of spectral calculation that uses some iterative algorithm, right? So it's a good ordering of these talks, as it turns out. So again, let's get a little bit more into the stochastic block model. You have an undirected simple graph, possible self-loops, okay? There's that many elements on a diagonal and above. Two blocks of size k and the floor of n over 2, right? So one's of size k, the other's nice k. And so we're going to be, stochastic block model is an instance of a random graph model. And there's two probabilities here. So PB is the between blocks, and we're going to always assume it's bounded from above by the within blocks, right? So again, this case is easy, right? I could permute this graph you could use almost any algorithm because in this case, the probabilities are quite distinct. So it's pretty easy to say whether you got two good blocks. So it gets more interesting when PB is close to PW. So let's set up the little bit of probability we'll need for that, right? So now I have these random variables, right? Because to get a realization of this random graph model, I'm going to have to flip coins, right? So I'm going to flip coins for these two blocks, right? And so the random variable can either take on a value of 1 or 0, right? It's a coin flip, okay? When PB is less than, strictly less than PW, then we know there's two blocks, okay? And so I just gave you a recipe on how to generate these graphs, okay? So now the thing you would do in classical statistics is you would basically pose a null and alternate hypothesis. So your null hypothesis is, you know what? The two probabilities are the same. There isn't two blocks in your data. There's just really one. And your alternate hypothesis, no. There's actually two, and the between block one is less, right? So within this lexicon, should we reject the null that there is only one block in favor of the alternative that there are two blocks, right? So we want to do this given a realization of the data, right? We're not assuming we know the answer. We want to, given an answer, determine whether it's correct or plausibility of it, right? So of course, there's errors that you can make with this, right? You can have a false positive, a false negative, right? For example, if the realization is drawn for one block and there's a small number of edges, then you're going to tend to reject the null hypothesis even when it's true. And that's in the literature called a probability alpha, and then the related problem of a probability beta. And then, so alpha is the size, and then 1 minus beta is what's called the statistical power, right? And that's our belief that correctly detecting that there are two blocks. So the idea would be some code says, here are the two blocks. We look at the data. We see whether that result is anything more than a random result. And if beta is small, right, then that means that's 1 minus beta is close to 1. So we have a pretty good insurance, right, with 98%. With 98% given the underlying model, for example, that you can trust the results, right? It doesn't say the results are correct. It's just saying, given the model, you can believe the result 98% of the time. Okay, but of course, the real trick and what a lot of people have studied is, what's the effect when these two go to 0? So again, PW is less than PB. So as they approach 0 from the positive size, what is dependence upon that and K, right? Because a lot of the analysis that's out in the literature considers a case where the two blocks are of equal size. So I wanted to, it turns out as I push through the analysis, you could actually vary that K. And I guess the point I'll make here also is that this sort of analysis may be new to you, but trust me, this is an elementary book in mathematical statistics. This is all kind of classical frequentist analysis. Okay, so what statistic am I going to use, right? I'm going to use this likelihood ratio, right? So I can count up the edges. And, for the two blocks, we're assuming that there's only one block. And look at the ratio, and then there's a big lemma called the Neyman-Pearson lemma that says that given a test of size alpha, okay, the most powerful statistic is this ratio, okay? And it turns out that if that ratio is equal to 1, that's going to be true if and only if the two probabilities are equal. If lambda is less than 1, then evidence is in favor of two blocks. If that ratio is larger than 1, evidence is in favor of one block, okay? Right, so what's well known statistically is that for fixed sample size n, as PW goes to BB, you're not going to be able to get a good size and good power, but by increasing the vertices, the number of vertices, increasing the data, or given that we have a random graph model, increasing the sample size, you'll be able to get a small beta and a small alpha, which is a good thing. So that's in a sense what a lot of this analysis revealed, is what are these ratios. So we just discussed this ratio, this binomial model, and it turns out that if you plug in those probabilities and you work through some analysis, you can show that the likelihood ratio is proportional to the number of edges between blocks. And this random variable is the number of edges and is given by this binomial distribution, right? So for this problem, right, you actually can solve this problem exactly. And this graph right here is just, if you just get on Wikipedia and you look up binomials, this is a classic problem in elementary statistics, is given that you flip a coin so many times, and so many heads come up, for example, and you knew that there was a possibility of two different coins with two different probabilities, based on just what you observed on the data, which coin would it be? So that's essentially how we were able to relate this graph partitioning problem to this sort of elementary analysis. Okay, but the situation in practice is somewhat more murky, because if you stop and think about it, the problem I looked at assumed that you knew a lot of things. You knew the size of the blocks. You knew which vertices were in which blocks. And in practice, if you knew that, you wouldn't be doing the analysis. You know the problem, right? So, but that was just to kind of set things up and to just kind of set up a straw man, right, to where you want to go. So instead now, what you want to use is the statistic. Well, what we're going to do now is, instead of separating into these random variables into two groups, we're going to just sum up all the places where there's ones, right? And there's n over 2 times n minus 1 of those, right? So just based on that number, okay, can we determine something, right? And it turns out this statistic has power when PW is less PW, but unfortunately, we don't know the distribution of that under the alternative, right? And this is kind of a little subtlety that, you know, if you add two normals, the means and variances add appropriately, but if you have two binomial distributions with different probabilities, they don't add quite nicely, right? So that's the reason why you don't know this null distribution. That would allow you to argue in what sense you can trust the data. So what do, right? So, you know, I came from a world, I still am in a world where if you don't know what to do, you integrate by parts. Well, you know, in statistics, if you don't know what to do, you use a central limit theorem, right? Okay. So it turns out that when these two numbers are not small, right, then you can invoke a central limit application. If you want to consider the more realistic case, that the probability is decreasing as the number of vertices increases, that would be a Poisson approximation, okay? But this sort of analysis we're using doesn't work in that case. So we're going to really just focus on a dense case. But it turns out that in the papers that I discussed, the ones that are doing hypothesis testing, the state of the art right now are results just for what amount to dense graphs, okay? So dense graphs doesn't necessarily mean that you look at it and it's dense. It just basically means that that is, you scale the number of vertices, the number of edges grows, stays fixed with that number, okay? So you can still get, in fact, you'll see confusion in the literature where they'll really have a dense graph, but they'll call it a sparse graph. So the field is still trying to find its way with respect to accepted terminology and understanding. Right, so the normal approximation, once we make this normal approximation, then we can push standard results through. This is a bit technical. The point is, once you've assumed you're in this asymptotic regime and these probabilities are not too small, then you have it's still a messy calculation, but it's doable. because you get to use a normal distribution, which you hear a lot of statisticians say what a wonderful thing the central limit theorem is. And when you actually have to do analysis that you get to use it, you do appreciate what an amazing thing that it is, okay? So again, I write down the size and power. So how would you kind of understand these size and powers? Because now you can provide confidence intervals, right? So based on the sample mean, right, you're just going to sum up all the entries in the upper graph, right, because they're either in the upper triangle of the adjacency matrix, they're either ones or zeros. So if you sum all those up, that's the sample mean. And now you can argue how accurate are. You can relate the size and power to these confidence intervals. So it gives you a good idea. And it also gives you a relationship. You understand what the effective n is. And it's quite, well, let me hold off on the thought I was going to make based on, let me just hold off here. And just the one thing that this previous slide was this z to the alpha over 2. The next picture is just reminding you what this might be. So that would be that area under the normal curve. So that's z sub alpha, and it would be 2.5, right? So if you wanted to know how much of the, what is the z-score for that, that's what it is right there. Give you some idea. All right, so we're nearing the end of the talk. Again, I write down the size and power for that, right? Where x is the average number of edges in the graph realization. And so now what's very interesting is you can actually get at this asymptotic, and you can get at this actually T alpha. And you can do a simple approximation to that, which is now bounded above for that. So basically, as n grows, it's with respect to the square root of this probability alpha. So that would tell you then that you sum up those x's when it's essentially less that value in the right, that's your statistical power, right? And so this critical value, this T alpha, is indeed small given a small size alpha because, well, you can do this approximation, all right? So again, if you haven't seen this sort of analysis before, you're probably not going to pick it up at the end of the first day in a conference, but this allows you to actually be very precise, because what happens is you'll basically pick an alpha, right? So somebody will say, well, I want to know with 2.5% accuracy, right? Well, 2.5% factor on the size. When I can, how small does that mean have to be before I understand what the size is? And this allows you to relate all that. And you can do the same thing for the power. And the 1 minus beta then tells you the power of the test, when you can actually accept the result that somebody gave you. Okay, and then you can do the same thing for the power pushed through the analysis. And this estimate is interesting because it actually allows you to see the effect of not only what happens when PW gets to close to PB, so as this probability of between, right, PW minus PB is positive, as the between block probabilities goes to the within block probabilities, 1 over the square root of that. That means in order to get a specified power of the test, n has to increase relative to that. And I think the comment I want to make here is in this work that James and Jeff did, they had a factor of n to the 1/2, and that's essentially right here. Because one of the questions I was going to ask you guys was, what is the effect of clustered eigenvalues, okay, upon your analysis? But this, in a sense, gets at it in a more visceral way, which instead of looking at the eigenvalues, it looks at the probabilities. But at the end of the day, it's a similar sort of thing. Thank you, Van. Oh, I only have one more graph to go. All right, and it also tells you gamma, okay. I've supposed that k, right, the size of the blocks are k and n minus k. So now just suppose gamma, k is some fraction of n. So I've just reparameterized k in terms of n. And so gamma can be 1.5 I also see that n grows as 1 over the square root of gamma. So if somebody tells you, or they want, if they believe they have a small block and then a remaining large block, in order to get a specified power, n is going to have to grow inversely proportional to the square root of that. And that's the first result that I've run across of that kind that gave you an understanding of what it means, of what these two disparate blocks says, right? All right, so at the end of the day, you may, you know, if you want to get a lot of power, given a small specified statistical significance, you're going to have to get a graph with more edges. You're going to have to sample more from your graph model. Okay, so summary. I like what James said at the end of the presentation of his works with Jeff, that it's often good to look at these simplified models because you get an understanding of what's going on, and it's interesting to see that you can apply what amount to elementary ideas from several different fields and put them together. And this is, in some sense, proof of principle, a proof of concept that you can actually consider this very interesting problem that when people say, here are the partitions, you can actually assess the results. Now, there are different results than the type of accurate results that I was used to in my previous life. These are more statistical, right? It's not necessarily saying you got the right results. It says, with respect to a statistical model, I can expect these results to be true, you know, 1 minus beta, 98% of the time, right? So are you a betting man, right? You know, it doesn't mean you'll always be right, but it's information you can pass on perhaps to an analyst who wants to understand their data about whether it's clustered. And that's the whole purpose of this, is to provide further information. And it also unearths a lot of the interesting issues, which then drives further more the mathematical analysis. So the hope is we can put something like this in these packages using doing computational spectrograph there to at least give some idea of how to assess the results. Thank you very much.
We have a couple of minutes left for questions, so if somebody has a question for Rich? Okay, well, they're dreaming up their question. Oh, here's one for Jane.
Your last bit about someone gives you an algorithm.
Speak so everybody can hear you.
Yeah. Could you imagine a way of certifying algorithms that they can recover this model well, often?
So you're saying, so I think you're asking, is the stochastic block model good for your data? No.
No, if I have an algorithm that claims to recover 2 blocks of stochastic block, and I give it to you,
yes.
could you
Exactly.
number of steps,
Yeah.
whether it does?
So, for example, a lot of these algorithms that determine these multiple communities, they look at the graph, they split it into 2 pieces, right? Then they cursively bisect. So now you could provide that for each of those pieces, and you at least argue, well, the split that we've introduced, this partition we produced, has this power, right? Given the stochastic, given the assumption of the stochastic block model, right? Exactly.
So let me ask you essentially the same question that Michaela asked James. Let us step into the world where things don't actually come from stochastic block models, and
They don't?
doesn't necessarily behave that. No, they don't.
Okay. All right.
Or if you will, step into the world where you walk into an analyst's office and say, I've done a bunch of statistical tests and I give you probabilities of how it's correct, and they throw you out.
Yeah.
What is the takeaway on how you would move from this regime to a regime based on, where you have much more complicated real world graphs and no ground truth to work from?
Yeah, so first of all, let's stop a minute and consider the stochastic block model. It gets picked on a lot, but It is underlying a deep result in graph theory called the Zemerati regularity lemma, which says that you can decompose any dense graph into a number of blocks where each of the blocks is regular, right? So there's actually a existence theory that says that the stochastic block model is not so made up. It does represent, it is in line with this regularity lemma. But now getting back to what you're saying, again, I understand your question. I guess what I would rephrase it is, right now we're in a situation where somebody tells an analyst or some code tells an analyst that here are 2 communities or 3 communities or 4 communities. There's nothing we can say. To be able to at least say that using things like the binomial theorem and the central limit theorem and even some random matrix theory, because those ideas are also used in these alternate papers, that you can at least provide some information along those lines is useful, right? So it's a start. That's all it is, yeah.